Well, hello everyone. Um, Welcome to, I guess this is part 4 officially of the Rust Roguelike tutorial. My name's Gary Mathis, software engineer. Using this tutorial myself to learn Rust. Um, yeah, anywho, let's get into this. Says the remainder of this tutorial will be dedicated to making a roguelike. Appeared in 1980 as a text mode dungeon exploration game, has spawned an entire genre of roguelites, procedurally generated maps, hunting on an objective over multiple levels, and permadeath, restart when you die. The definition uh, is the source of many online fights. I'd rather avoid that. Um, a roguelike without a map to explore is a bit pointless. So in this chapter, we'll put together a basic map, draw it, and let your player walk around a bit. We're starting with the code from chapter 2, but with the red smiley faces uh, and their leftward tendencies removed. Okay, so looks like it's wanting us to remove all of, yeah, it wants us to remove the rendering, so we're going to get rid of this right here is left walker, yes. So we're going to get rid of left mover, left walker, we're going to get rid of this, and I think at this point we can get rid of this. Our player, we want that. If we want to get rid of left mover, if we save this and try to run it, left walker, oh, left rotation of state. Does this actually run now? Systems, actually we'll add that. We're going to get rid of, I don't know, we're going to want this later. Okay, so there we are. Game runs. No longer red smiley faces all over the place. That's cool. Alright, so defining the map tiles. We'll start by allowing two tile types, um, walls and floors. We can represent this with an enum to learn more about enumerations. Uh, the Rust book has a large section on them. Alright, so imagine that enum is just like any other enum in any other programming language, so I'm not going to delve into that. So I want to go ahead and define my enums above my structs. And it looks like we're going to derive a few things. Partial equality, copy, clone, and we're going to say enum tile type wall 4. Looks good to me. Notice we haven't included that we've included some derived functions, more usage of derived macros. This time is built in the Rust itself. Copy and clone. Clone adds a clone method to the type, allowing a copy to be made programmatically. Copy changes the default from moving the object on assignment to making a copy. So tile 1 equals tile 2 leaves both values valid and not in a moved from state. Partial equal allows us to use the equal equal to see if two tile types match. If we didn't derive these features, tile type equals tile type wall would fail to compile. Okay. So partial equal, that makes sense. Building a simple map. Now we'll make a function that returns a vector of tiles representing a simple map. We'll use a vector sized to the whole map, which means we need a way to figure out which array index is at a given xy positions. So first we'll create a new function xy index. So I am going to put this above player input. This looks like it's going to be pub, and xy idx, X I32, Y I32. I don't think it really matters. U size. Y as U size. Oh, I don't like casting, but we're doing it anyway. 80 plus X as U size. Surprised we're not using U size here if it's integer 32, but maybe Rust handles U sizes a little bit different. And I don't like how this declaration is going to be here, so I'm going to use the C syntax of it. Okay. This is simple. It multiples the Y position by the map width 80 and adds X. This guarantees one tile per location and efficiently maps it in memory left to right reading. Okay. Using a Rust function shorthand here. Notice the function returns a U size equivalent to size T in C, C++, whatever basic size type for a platform is. And the function body lacks a semicolon at the end. Any function that ends with a statement that lacks a semicolon treats that line as a return statement. So as the same as type and return. Okay. Yep. This comes from the Rust author's other favorite language, ML, which uses the same shorthand. It's considered Rustacean, I don't know, canonical Rust. I always picture a Rust monster with a cute little claws and shell to use this style, so we've adopted it for this tutorial. Yeah, I'm not going to adopt it myself. Then we write a constructor function to make a map. Alright, so we're going to say fn new map. Vec tile type. Let mute map vec macro. Okay, type. 80 times 50. Okay, so 80 times 50, floor tile, 4,000 tiles is what we're generating here of type floor. Makes sense. For x in 0, 80, whoops, map xy idx x0 equals tile type wall map idx x49 equals tile type. Doing wrong here. Mesh types, expected vec tile type found. I think it's a big, okay, it's because we should be returning map down here. Okay. I was wondering why it was erroring out on that function. Okay, no other language does that. For y in 0, 50 map xy dx 0 y plus tile type all map xy dx is it 79 y plus tile type. Perfect. And so that this makes boundaries, right? And then random walls. RNG, RLTK random number generator new for I in 0 400 x equals rng dot replace 179 rng dot roll dice 149 idx equals xy idx xy of idx 4025 map idx equals tile type wall. Alright, so this should be generating the random walls. That's cool. There's a fair amount of syntax that we haven't encountered here before here, so let's break this down. Function newMap vec tile type specifies a function named newMap. It doesn't take any parameters, so it can be called from anywhere. It returns a vec. Vec is a rest vector. If you're familiar with C++, it's pretty much exactly the same as C++ standard vector. A vector is just like an array, which lets you put a bunch of data into a list and access each element. Unlike an array, a vec doesn't have a size limit, and the size can change while the program runs. So you can push and add new items or remove them as you go. Rust, by example, has a great chapter on vectors. It's a good idea to learn about them. They're used everywhere. Okay, so this is really dynamically sized array using the heap rather than the stack. It's really what that's talking about. Really becomes more important when you get into lower level systems languages because you have to define things like malloc and free and stuff like that. So let mutable map equal vec tile type floor 80 by 25 is confusing looking statement. Let's break it down. Let map is saying make a new variable. Let me change. Mute call it a map. And vec is a macro. Another one built into the Rust standalone library or standard library. The explanation part, Marcus Rust's way of saying this is a procedure macro as opposed to derived macro like we've seen before. Procedural macros run like a function. They are defined. They define a procedure. They just greatly reduce your typing. The vec macro takes a parameter in square brackets. The first parameter of the value is the value for each element in a new vector. In this case, we're setting every entry we create to be a floor from the tile type enumeration. The second parameter is how many tiles we should create. They should also they will also set the value we set above. In this case, our map is 80 by 50 tiles, 4,000 tiles, but we'll let the compiler do the math for us. So we need to make 4,000 tiles. Um, excuse me. You could have replaced the vet call with a for I am 4000 map push tile floor. In fact, that's pretty much what the macro did for you, but it's definitely less typing to have the macro do that for you. For x in 080 is a for loop, so here we just use the previous example. In this case, we're iterating x 0 to 79. So here we're looking at the map. It's a lot of reading. First, we call xyidx function defined above, get the vector index for x0, then it then indexes the vector, telling it to set the vector entry point at that position to be a wall. We do this again for x49. We do the same thing, but looping for y, 049, setting the vertical walls on our map. Let mute RNG, RLTK random number generator new calls a random number generator type in RLTK's new function and assigns a variable we call it RNG. We're asking RLTK to give us a new dice roller. Okay. For underscore I 400 is the same as the other loops, but notice the underscore before I, we aren't actually looking for the value of I, we just want the loop to run 400 times. Rust will give you a warning if you have a variable you don't use. Adding the underscore prefix tells Rust it's okay. We meant to do that. Let X RNG roll dice calls RNG. We grab in 7 and ask for a random number 1 to 79. RLTK does not go with the exclusive range because it's trying to mirror the old D&D convention of rice being 1d20 or similar. In this case, we should be glad that computers don't care about the geometric difficulties of inventing a 79-sided dice. We also obtain a Y value 1 in 49. We rolled imaginary dice and found a random location in the map. Okay, that's fine. We set the variable IDX, short for index, to the vector XY index we defined earlier and the coordinates we rolled. If IDX checks IDX's exact middle, we'll be starting there, so we don't want to start inside of a wall. If it is in the middle, we randomly we set the randomly rolled location to be a wall. It's pretty simple. It places walls around the outer edges of the map and then adds 400 random walls anywhere the player isn't at the starting point. Okay. Making the map visible to the world. Specs includes a concept of resources, shared data the whole ECS can use. So in our main function, we'll add a randomly generated map to the world. Okay. So there's map. We'll go into the main function here, and there's that GS ECS register. We'll go ahead and GS ECS insert new map. The map is now available from anywhere anywhere the ECS can see. Now inside of your code, we can access the map with a rather unwieldy let map self get mutation. It's available to systems in an easier fashion. There's actually several ways to get the value of the map, including ECS get, ECS fetch, get mute obtains a mutable, so you can change it reference to map wrapped in an optional. In this case, map isn't here. Fetch skips the option, gives you map directly. You can do more, read more about this in the specs book. So if I just run here, we should still run. Gives me the same. So for now, in memory, we should have a map generated. We're just not. Drawing it yet. Okay, now that we have a map available, we should put it on the screen. The complete code for the new draw map function looks like this. Okay. That new map. There's a state. There's the tick. We'll do fm draw map. Whoops. And we'll say map tile type. CTX is a mutable reference to RLTK. Okay. And we'll say let mute y equals 0. Let mute x equals 0. And we'll say for tile in map dot iter match tile type floor ctx dot set y rgb 0 0 whoops. Okay. And we'll zero 0, 0, ILTK dot 2 CP 437 dot dot. Okay, and then we'll do tile type dot wall 0, 1, 0. And 0, 0, 0, and we'll put hashtag. Alright, so and then we move the coordinates, right? We switch coordinates, and I think this is in the for loop. Yeah, it's just below the match. X plus equal if x is greater than 79. This is mostly straightforward and uses concept we already visited. In the declaration, we pass the map tile type rather than vec tile type. This allows us to pass in slices parts of a map, so we can, if we choose. We won't do that yet, but may be useful later. It's also considered a more rustic, that is idiomatic rust and way to do things. And the linter Clippy warns about it. Okay. Otherwise, it takes advantage of the way we are storing our map rows together, one after the other, so it iterates through the entire map structure, adding 1 to the X position for each tile. If it hits the map width, it zeroes out and adds 1 to Y. This way we aren't repeatedly reading all over the array, which can get slow. The actual rendering is very simple. We match the tile type and draw either a period or a hash for walls and floors. We should also call the function in our tick. Okay, let map. Okay. Do that right after the clearing of the screen. So now, yeah, this should be a path separator. It should be RGB. My bad, I'm used to programming in other languages. Give that another shot. Okay. Expected 1 argument, supplied 3 arguments. Oh, from F32. So we do need those dots, I think. Can I do... No. Anywhere where... Okay. Oops. Alright, player input self CTX, immutable borrow occurs here. Change anything else. There we go. There's our map. It's being drawn now. Good. Alright. Otherwise it takes advantage. Okay, we've already done this. The fetch call is new. We mentioned it above. Fetch requires that you promise that you know what the resources you're requesting really does exist, and will crash if it doesn't. It doesn't quite return a reference. It's a shared type, which acts like a reference most of the time, but occasionally needs a bit of coursed, I don't know how to say that, coursing, whatever, to be done. We'll worry about that bridge when it comes time to cross it, but consider yourself warned. Okay, it's talking about fetch here. Okay. making walls solid. So now, if you run the program cargo run, you'll have a green map with a yellow at, and you can move around. Unfortunately, you'll quickly notice the player can walk through walls. Fortunately, that's pretty easy to rectify. To accomplish this, we'll modify the try move player to read the map and check the destination is open. Okay. So the try new player or try move player, it needs a reference to the map. So const or let map equal ECS dot fetch the vec tile type. All right, and it says for player position, and we'll say destination x equals xy position dot y plus delta should be x position dot x delta x, and then position y delta y. All right, and we'll say if map destination index is not equal to tile type wall, this right here, this extra parentheses not needed, I don't think. And now if we try to run it, does it run? Sure does. Can I move? No, we cannot walk through walls anymore. It's great. And I honestly don't think we need, if we're having borders around, we don't need them in max anymore. But all right. This new the new parts are the let map part, which uses fetch just the same way the main loop. This is the advantage of storing it in the ECS. You can get it everywhere without trying to course Rust into letting you use global variables. We calculate the cell index to the player's destination, let destination, and if uh, this isn't a wall, we move as normal, run the program, and you will have a player on the map. You can move around properly obstructed by walls. The full program now looks like this. Okay. And then, of course, we can have something that looks very similar. Just a randomly generated map, though. Yep, that's what our map looks like. It looks good. I like to play around with it a little bit. All right. So we have officially walked a map. Awesome. Well, thank you guys for watching. We've officially walked the map, and the next video we're going to look at just a more interesting map. It looks like. All right. Thank you guys again for watching. Have a good one.